Hello students. So up till now we have discussed about D block elements. Today we are going to study about F block elements. F block element is actually extension of the periodic table, lanthanum to lutetium and actinium to lawrencium. So this is first series of F block and this is the second series of F block. The first series is called as lanthanoids because they follow lanthanum. The second series is called as actinoid because they follow actinium. If I correlate them to number of periods, so lanthanum belongs to 6th period, it is extension part, and actinoids belong to 7th period. So I will say n equals to 6 for lanthanoids and n equal to 7 for actinoids. So in today's video we are going to discuss their properties, their uses and some other special phenomena related to it. So let us begin the studies of F block elements, also commonly called as inner transition elements. We have seen that D block elements are called as transition elements and F block elements are called as inner transition elements. Now the reason why F block elements are called as inner transition elements, because the last electron that enters in 4f subshell, and we know 4f subshell is anti-penultimate shell, or we can also call it as pre-penultimate shell, and therefore they are called as inner transition elements. F block elements have two series, lanthanoids and actinoids. Lanthanoids, they are also called as 4f series, as the electron enters, especially the last electron enters in 4f subshell, whereas actinoids, it is called as 5f series, as the last electron enters in 5f subshell. Lanthanoids, as we have seen just now, starts from lanthanum and extends till lutetium with atomic number 57 to 71. Whereas actinoids, it starts from actinium and ends at lawrencium, the atomic number varying from 89 to 103. Lanthanoids are also called as rare earth elements, as they exist in the earth rarely. The general configuration of F block elements is n-2 F 1 to 14, n-1 D 0 1 ns2. So just now we have seen that last electron will enter in anti-penultimate shell, that is F shell. So with this basic knowledge we will study first of all lanthanoids. So in lanthanoids n equals to 6. Using general configuration we will decide the configuration of lanthanoids. It is 4F 1 to 14, 5T 0 to 1, 6S2. So this is the configuration of lanthanoids. Now we will study various trends in lanthanoids. The first we are going to discuss atomic and ionic radii, what is called as lanthanoid contraction. Now this topic is very important one, and a direct question is asked, what do you mean by lanthanoid contraction, what are its consequences, etc. So what is lanthanoid contraction? Steady decrease in atomic and ionic sizes of lanthanoid elements with increase in atomic number, that is what we call as lanthanoid contraction. We will study the cause of this lanthanoid contraction. Now as we move from left to right, what will happen? The nuclear charge will increase by 1 unit. But we have to pay attention to the electrons added. The electrons, they are added in same inner 4f subshell, and therefore that will have an impact on the size of atomic and ionic radii. How? 4f subshell, they offer very poor shielding effect. So the new electrons are getting added more and more in 4f. But due to poor shielding effect, effective nuclear charge experienced by this 4f electron will increase. As a result, what will happen? The 4f subshell will contract. More and more electrons getting added to 4f, more and more effective nuclear charge it will experience. More and more there will be contraction, and that is what we call as lanthanoid contraction. So due to decrease in the size of 4f, due to contraction of 4f, the atomic and ionic sizes of lanthanoid elements decreases with increase in atomic number. So what is the consequences of this lanthanoid contraction? The very first is resemblance of second and third transition element. As a result of lanthanoid contraction, the atomic sizes of second and third transition series they become almost similar. I will show you the example. As you can see in the periodic table, this is the second transition series and this is the third transition series. Especially zirconium and hafnium, they will have similar sizes, as hafnium is placed just after lanthanoid elements. Lanthanoid elements, they will have their own contraction called as lanthanoid contraction. Therefore, hafnium will be also become small in size, and as a consequence, zirconium and hafnium will show similar sizes, which is one of your important give reason question. The lanthanoid contraction and its consequences, generally they are asked for 3-mark question. Definition can be also asked separately. Let us move on to the next consequences. So what we have seen, due to lanthanoid contraction, all the lanthanoid elements shown here about the same size, and therefore what happens, their properties becomes similar. As a result, the lanthanides show similar property. It is very difficult to separate them. So only method available to separate them is ion exchange method. This method only can be used to separate. The next consequence of lanthanoid contraction is the difference in basicity of oxides. The basic strength of oxides decreases. With increase in atomic number. So overall, if I compare the basic strength of oxides of lanthanoid elements, then we can see lanthanum hydroxide will be more basic than lutetium hydroxide. Again, I will say this question is important give reason question. The next consequence is covalent character, or I will say covalent property of cation increases. Moving on to the next consequences, the complex forming ability of lanthanoid elements increases from lanthanum to lutetium as a result of lanthanoid contraction, especially in their ionic state. I will say lutetium 3+, they will form complex more easily. Complex formation more easily as compared to other elements due to very small size and high density. These consequences are asked as a direct question. Let us discuss the next trend, oxidation state. Now if we look at the configuration of lanthanoids, it is xenon 4F 1 to 14, 5D 0 to 1, 6S2. Now this 4f orbital, it is very deeply situated and therefore it cannot participate in bonding. So which orbitals are available for bonding now? 5d and 6s. So one electron from 5d and two electrons from 6s can be removed, and therefore the stable oxidation state of lanthanoid elements is +3. Remember this concept. The stable oxidation state of lanthanoid elements is +3. But there are certain exceptions also, like terbium sometimes shows 4+, cerium exists in 4+, as well as praseodymium. It also exists in 4+, and therefore they act as good oxidizing agents. Why? Because they get converted, or I will use the word, they will get reduced to their stable +3 oxidation state. Similarly, if we look at the other elements like samarium 2+, ytterbium 2+, and uranium 2+, they will act as good reducing agent. Why? Because they will get oxidized to their stable +3 oxidation state. Now this stability comes because of half-filled or fully filled f orbital. We can also say half-filled, fully filled, or vacant f orbital. Now especially this cerium 4+, many a time question is asked that why cerium 4+ is a good oxidizing agent. Why it is a good analytical reagent? Because it easily gets reduced to its stable oxidation state, that is +3, and therefore its E0 value is also in positive. Its E0 value is +1.77 volt. The other characteristics of lanthanoid elements include their nature. They are silver, white, soft metals. They easily get tarnished in air. The hardness increases with increase in atomic number. Third ionization enthalpy is low, especially for lanthanum, gadolinium, and lutetium. And this will indicate the degree of stability for empty, half-filled, or fully filled f orbital. Generally, they have negative E0, showing that they are good reducing agent. Comparatively, they have large size, so they cannot polarize neighboring ion or molecule. Similarly, they show colors. As we have seen that D block elements show color, F block elements, lanthanoids, they also show colors, and the reason is FF transition. Like we have seen in case of D block elements, DD transition. In case of F block elements, it is FF transition. But the condition is that F block must be incompletely filled. If there is F subshell, if it is fully filled or if it is vacant, then it will not show any color. Example, lanthanum 3+, lutetium 3+. Similarly, all lanthanum ions are paramagnetic except cerium 4+, lutetium 3+, and ytterbium 4+. The reason lies in their vacant and fully filled f orbital. Let us move to its chemical properties. So I have tried to show all the chemical properties in one flow chart. To complete this flow chart, we have to remember that the stable oxidation state of lanthanum is +3. Okay, so lanthanum, if it is burnt in air, it will form lanthanum oxide Ln2O3, any element of the lanthanoid series. Now if it is heated with nitrogen, it will form corresponding nitride. If it is heated with halogen, it will form corresponding halide. If any lanthanoid element is heated with carbon, then it can form variety of compounds like Ln3C, Ln2C3, LnC2, etc. Now if any lanthanoid element is heated with sulfur, it will form corresponding sulfide. Lanthanoid element, when treated with acid, they releases hydrogen gas. And lastly, when lanthanoid elements are treated with hot water, it forms lanthanum hydroxide and hydrogen gas is released. Now the question is, why we need to study these lanthanoid elements? Are there any uses of lanthanoid in daily life? So now let us see its uses. In the uses of lanthanoids, the most important use is mesh metal. Many a time asked question. Direct question. What is a mesh metal? Mesh metal is actually alloy. Alloy of lanthanoid, where lanthanum is present in 95%, iron 5%, and traces of other elements like sulfur, carbon, calcium, aluminium, etc. So using all these elements, an alloy is made which is known as a mesh metal. Now this composition was once asked in JEE. Now where this mesh metal is used, it is actually pyrophoric alloy. That means it can produce spark when scratched with steel or some other elements, and therefore it is used to produce bullets, lighter flint, etc. The second use of lanthanoid is the mixed oxides of lanthanum are used as catalyst in petroleum cracking. So this was all about lanthanoids. Now we will study actinoids. So actinoids, they start from actinium and ends at lawrencium, atomic number 89 and that of lawrencium 103. So we have also seen that it's a 5F series. So using that we'll calculate its general configuration. Its general configuration will be 5F1 to 14, 61, sorry not 6S, 7S2, 60, 0 to 1, and the nearest noble gas is radon. So this is the general electronic configuration of actinoids. Now let us study its strengths. The first strength, atomic and ionic sizes. Like lanthanoids, actinoids also show contraction. So steady decrease in actinoid series we call it as actinoid contraction. But the magnitude of actinoid contraction is comparatively greater than that of lanthanoid contraction. Reason lies here. The electrons are filled in 5F orbital. So 5F subshell, it is larger in size, offers very poor shielding effect, and therefore contraction of actinoid becomes larger than that of lanthanoid contraction. The actinoid contraction becomes larger than that of lanthanoid contraction. I will say it is important. Give reason question. So now next trend that we'll be studying is oxidation state. But before we study oxidation state, have a look at its configuration. 5F, 6D and 7S. 5F is not deeply situated as compared to 4F, and therefore the oxidation states shown by actinoids, they are variety of oxidation states. So due to less energy gap between 5F, 6D and 7S, all these can participate in bonding. Which is not a case in lanthanoid elements, and therefore actinoids, they can show oxidation states like +3, +4, +5, +6, etc. Whereas in case of lanthanoids, it is only 1 +3. This point is important. Give reason question. That why actinoid shows more number of oxidation state as compared to that of lanthanoids. Moving on to the next property, color. Most of the actinoids, they are colored compounds. Again I will say due to FF transition, but there is exception. Actinium 3+, cerium 3+, and thorium 4+. curium. The reason lies in their electronic configuration. Actin 3 plus shows 5f0, that is vacant F. Curium shows 5f7 and this thorium shows again 5f0 configuration, and therefore these elements are colorless elements. The interesting thing about actinoids is all actinoid elements, they are radioactive, whereas lanthanoid elements, they are not radioactive. So this is a point of difference between actinoids and lanthanoids. Similarly, these actinoids, or I will say oxides of actinoids, they are more basic as compared to lanthanum oxides. Actinoids, they have greater tendency to form complexes. Why? Because this 5F, 6D and 7S can easily participate in bonding. So that was all about the study of lanthanoids and actinoids. One common question asked for lanthanoids and actinoids is find out the similarity and differences among lanthanoids and actinoids. So assignment for today is this question: similarity and differences among lanthanoids and actinoids. With this session, we have completed studies of D block elements as well as F block elements. D block and F block elements are important and logical chapter with respect to give reason question, with respect to complete the equation question, with respect to word problems, etc. That's all for the day. Thanks for watching. Have a nice day.